Good morning, all, and welcome to the final session of our anti-and wave propagation online classes. As of now, like, as per the current information, this will be the last class. So, our topic we are going to finish off with this 1 hour lecture. Okay. So, we will start from where we are left yesterday. So, we are discussing about patch antennas. Okay. So, in patch antenna, we already saw the microscope or patch, and in that we already saw the design and patch parameters, all those things. Now we will move on to an effect called fringing effect. Okay, this is just an effect which occurs in the smart antenna based on the dielectric we are using, okay, or substrate we are using. So we will just see what it is. Dimensions of the patch are finite along the length and width. Okay, that means patch is a solid material. Okay, should I told about etching and all? So it will be etched out. So this its dimensions are fixed. It is solid material. Okay, but fringing means some sort of expansion while we are using. Okay, in effect, there can be some sort of expansion of the material, but the material will be solid, but like we may feel like the material has been expanded. That is the basic idea behind this. Okay, so you will see the amount of fringing is a function of dimension of the patch and height of the substrate. Fringing means it is sort of expansion. Okay, actually it is not expanding, but we will feel like it is expanded. Okay. So that expansion, that will be a function of dimensions of patch and height of the substrate. Okay. Fringing makes the microstrip look wider electrically compared to its physical dimensions. That's only I was like explaining. Okay. It makes the microstrip look wider than its physical dimension. Okay. Electrically wider. That means whenever it operates at that time, we may feel like its size has become large. Some of the waves travel in the substrate and some in the air. Okay, that is the basic cause of this fringing. We are having a microstrip antenna located in a substrate. Okay, so the waves which the antenna emits are supposed to travel through the substrate because field lines are provided through the substrate only. Okay, but some of the waves will travel through the air and then it will come to the substrate. So the smaller the relative permeability or dielectric constant ER, the more bowed the fringing fields become. They are extended away from the patch. It means for smaller epsilon r, the fringing field or fields which are coming outside and which are traveling through the air, that will become more bowed. Therefore, more bowed means more bended. Okay. Therefore, using a smaller permittivity for the substrate yield better radiation. So, if you are using a small permittivity, what will happen? The fields will more bowed and more it will travel through the substrate. That is only desired. So, using a smaller permittivity for the substrate yields better radiation. I will just explain that with a figure. Then you will get a better understanding. Okay. See, this is the patch antenna we are having. Okay, this is the patch antenna we are having. Actually, these are the fields. These arrow marks are the fields. Actually, these fields are supposed to travel through the substrate. Okay, but these fringing fields, which are traveling through the air and then it will enter in the substrate. So, whenever we are looking from the substrate, we will feel like actually this is this much width only. Actually, this strip antenna, microstrip antenna is having this much width only. But when it operates, we may feel like it is having width from here to here. That is due to this fringing fields. Okay, that's the problem with the fringing effect. So what is the solution for that? What we can use? We can use a medium with lower epsilon r, so that this will become more bowed. Bowed means this bending become more sharp. So that will adjust for the fringing fields. So the fringing won't be that much severe. Okay. So it will bend like this. So the fringing will be minimum. Okay. So that is the remedy for this fringing effect. Okay. So these fields are called fringing fields, which are traveling through the air and then enters into the substrate. Okay. This is just a simple concept only. Just understand that. That's all. Okay, next we are moving on to the feeding techniques used in microstrip antennas. Okay, there are different types of feeding techniques which we are using to feed the microstrip antenna. That we will see one by one. Just the basic thing about the feeding techniques is you should understand the diagram. That's all. The rest of the things you can write on your own. Okay, but without the diagram, if you are writing everything, that doesn't have a value on examiner point of view. Okay. In exams and all, these diagrams are very, very important. And you should draw it correctly also. It is not like that you should draw something and explain something. You should draw the correct figure. That's it. 50% or 60% of marks already scored if the diagram is correct. Because if the diagram is correct, your explanation will also be correct automatically. Okay. So that's the importance of diagrams in examinations. Okay. So we will see. First one is microstrip line fixed. You will see what is that. A conducting strip is connected directly to the edge of the microstrip patch. This is basic simple thing that we can expect. The patch antenna, this patch antenna you can see here, this patch antenna directly a microstrip feed line or feed line is directly connected to the patch antenna. That's it. There is nothing complicated. This is the patch antenna. Patch is shown as patch. Okay, this is the patch antenna. For this antenna, we are giving feed from directly through a microstrip feed line. We are giving the feed. That's all. And it will be having ground plate, and on the ground plate, the electric substrate will be there. And patch antenna, as we already see, patch antenna will be photo etched above this substrate. Okay, so this is the patch antenna, and this is the microstrip feed line. So is it easy to fabricate? Yes, it is easy to fabricate. The spurious radiation is low. That means the radiation which is going outside, that will be low. And the one disadvantage is there, this bandwidth is narrow. We cannot use this type of feed techniques for a large bandwidth. Okay. So this is just characteristic you can understand. The main thing is understanding the diagram and explaining the thing. Okay. So next one is the coaxial feed. Coaxial feed means you already know. Yesterday we have discussed about coaxial cable and all. Okay. There will be two wires on the same axis. So one outer conductor and one inner conductor. Okay, that is the coaxial cable. So we will see what is coaxial feed for a microstrip antenna. In coaxial feed, the inner conductor of the coaxial penetrates the substrate from the back of the ground plane without any contact with the ground plane and is attached to radiation patch while the outer conductor is connected to ground plane. Okay, that is shown here. This is the ground plane. Above the ground plane, the electric substrate will be there, and on the substrate, microstrip patch will be there. Okay, that is the basic construction of a patch antenna. So, in coaxial feed, one coaxial connector will be there or coaxial cable will be there. In that, the inner conductor that will go directly to the microstrip patch. Okay, that won't having any contact with the ground plane, and the outer conductor will be connected to ground plane. This is the feed techniques. This is the coaxial feed technique. Here also it is easy to fabricate. Spurious radiation is low, narrow bandwidth. It is same as the characteristics are same as the first one. Okay, microstrip line feed and coaxial feed are having same characteristics. The thing is here that is a coaxial cable. There it is a microstrip line. Okay, in place of microstrip line we are using coaxial cable. That's the only difference, actually speaking. But since we are using the coaxial cable, we have to connect the second end also. So the second end is connected to the ground plane and the inner core or the inner conductor that is connected directly to the microstrip patch. Okay, just we are doing in the coaxial cable of CRO. Okay, CRO, the outer cable, we will just connect to the ground. The inner cable only we are going to feed to our desired portion. Okay, same idea only here also. Can relate like that. And third one is aperture coupled feed. Okay, we'll see what it is. It consists of high dielectric material for the bottom substrate and thick low dielectric material for top substrate. Here substrate itself is divided into two. Okay. A high dielectric material for bottom substrate and low dielectric material for top substrate. Two substrates are separated by a ground plane. Here the ground plane is in between these two substrates. Okay. On the bottom side of the lower substrate means high dielectric material. Okay. On the bottom side of the lower substrate, there is a microstrip feed line whose energy is coupled to patch through a slot on the ground plane separating the two substrates. Bottom side of the lower substrate, the microstrip feed line is there. Okay. And which is coupled to the patch, which is coupled to the antenna through a slot on the ground plane. Ground plane lies between these two substrates. Okay. So we will make a slot in the ground plane, and from that, this feed line, which is lies on the bottom side of the lower substrate, is coupled to the patch. The characteristics are: ground plane isolates feed from radiator and minimizes interference. Okay, that is the very big advantage. Here, below the ground plane only, we are having this feed line. So, whenever the antenna is radiating, it will not interfere with the feed line. Okay, and low bandwidth, of course, it is more difficult to fabricate since we have to arrange these two substrate, and in between you have to place the ground plane, and from the ground plane we have to make a slot, and we have to connect to the patch. Means that will be difficult to fabricate. Okay, so we will see the diagram of that. See here, that shows here. Okay, so this is the lower substrate, this is the upper substrate. Okay, as you can see here, two dielectric material, high dielectric material for the bottom substrate and low dielectric material for top substrate. Okay, this is the low dielectric material, and it will be thick also. Okay, just remember this diagram and you can write everything. Here, this will be low dielectric material and that will be thick. Okay, here that will be high dielectric material and that will be thin. Then in between those two, the ground plane is there. Okay, and then on the bottom side of the lower substrate, there is a microstrip feed line. That feed line, it is the lower surface of the lower part of the bottom line of the lower substrate. Okay, that is that's why it is shown as the dotted line. So I think in between so many people are joining and leaving. So I'm getting notifications every now and then. Okay. Anyway, so that is only it is showing us dotted line. So this is the patch antenna, and the slot will be made on this ground plane. So that will not be visible since the this substrate is here. So that's also shown as dotted line. That is a slot. So that's all. That's all about the aperture coupled feed. Okay. So in this, you have to remember one thing: ground plane isolates feed from the radiator, so the interference will be minimal, and the bandwidth will be low, and of course, it is more difficult to fabricate. Next one is the proximity coupled feed. Okay. Here, two dielectric substrates are used such that feed line is between the two. That is there lies the difference between proximity coupled feed and aperture coupled feed. In aperture coupled feed, feed line was bottom part of the lower layer. Okay, but here feed line lies in between the two substrates, and the radiating patch is on the top of the upper substrate. Okay, we will see just the diagram of that. See, here there is no ground plane in between. Okay, one lower substrate is there, one upper substrate is there. Both are having same thickness. Okay, and feed line is in between these two. Between this epsilon r1 and epsilon r2, the feed line is there. So here no slot is there. Okay, so from here, this microstrip line, it is directly connected to the patch. The microstrip line lies in between these two layers. Okay. So characteristics are: it is having highest bandwidth. impedance matching controlled by the length of feeding step. So the disadvantage is inefficiency and very narrow bandwidth. So that is the total disadvantages. Okay. Highest bandwidth means within this patch antennas. Within this patch antennas, this proximity coupled feed, this is having the highest bandwidth. And generally, we are talking these patch antennas are having very narrow bandwidth, and their efficiency is also very less. Okay, so that's all about the feeding techniques, and these are some design parameters. Okay, so this just you can remember the equations if one. That's all. Other than that, design one, I think only once it has been asked in university examinations, but it is practically very difficult. I think that question got cancelled also later. So designing of patch antenna, that is somewhat difficult. Okay, it is some lengthy calculations are required for it. So this is the basic design equations: width of the patch, effective dielectric constant of the patch, extended incremental length, actual length of the patch. These are all the design parameters we need to calculate if we want to design the patch antenna or microstrip antenna. Okay, so I think that's all about the patch antenna or microstrip antenna. Now we will I will just show you one microstrip antenna. Like yesterday I told, this is the most commonly used thing and all. So this is just an example of a microstrip patch antenna, old Nokia handset, I think, or Reliance, I don't know. In that, microstrip patch antenna is there, and it was having, see, television receiver. Okay, these arrays are used in satellite television receivers. So this is the array of microstrip antennas. Okay, so like this much space is only required for that. I think you might have seen this in PCBs and all, like if in your satellite television receivers, set-top box and all, you can see this. Okay, and in all the dish antenna, all the dish TV receiver, in that, if you are opening that receiver inside, you can see this. Okay, so if you observe this, it's good. Otherwise, okay, just now you can see. So that's all about the microstrip antennas. Now we are moving on to smart antennas. Okay, so smart antennas are recent developments. Recent means comparatively recent. Okay, antenna arrays with smart signal processing algorithms used to identify the direction of arrival of the signal. Direction of arrival is DOA, it's abbreviated as DOA, and use it to track and locate the antenna beam on the target. Okay. So these smart antennas are nothing but they are having some signal processing algorithm, and with that algorithms, they will identify the direction of arrival of the signal. Okay. Then, if once we are located the direction of arrival of the signal, we can use it to locate the antenna beam on the target. We are having on target, from there we are receiving a signal. So we want to focus our antenna beam onto that target. So if we are able to identify the location of the target by using subsequent processing algorithms, we can easily identify the direction, and we can point our antenna beam into that particular target. Okay, so our directivity will be more. While the main purpose of standard antennas are to effectively transmit and receive radio signal, there are two additional functions that smart antennas or adaptive antennas need to fulfill. Okay, that is main thing. Main purpose of normal antennas or standard antennas are just effectively transmit the signal and effectively receive the signal. That's all. But in smart antennas are also called as adaptive antennas. Additionally, they have to do two more functions, or they need to fulfill two more functions that we will see. First is the direction of arrival estimation. In order for the smart antenna to be able to provide the required functionality and optimization of the transmission and reception, they need to be able to detect the direction of arrival of the required incoming signal. Suppose I am having a smart antenna here, and it is getting a signal from a particular direction. It is not previously known from which direction the signal is coming. The antenna is just receiving a signal from some direction. But since my antenna is a smart antenna, it is having some signal processing algorithms inbuilt so that the antenna can calculate from which direction the signal is coming, and it can orient towards that direction. So the better reception and better radiation can be achieved. Okay. The information received by the antenna array is passed to the signal processor within the antenna, and this provides the required analysis, just I told. Okay. Second one is the beam steering. Okay, I already told two additional requirements needs to fulfill for the smart antenna. First one is the direction of arrival estimation. It should estimate from which direction the signal is arriving or which direction the receiver is located. Okay, and after locating that, it has to do beam steering. Okay, I told I am having one antenna here and it is receiving signal from somewhere. The direction is unknown. But since the antenna is a smart antenna and it is having an inbuilt algorithm to locate the direction of the radiation, it will identify from which direction the radiation is coming or at which direction the receiver is located. Okay. The next is beam steering. After locating, second one is the beam steering. With the direction of arrival of the required and any interfering signals analyzed, the control circuitry within the antenna is able to optimize the directional beam pattern of the adaptive antenna array to provide the required performance. Okay. So suppose my antenna located that the receiver is on the left side. Antenna is located while receiving the signals. Antenna is located. The receiver is located on the left side, but it was actually positioning towards the front side. Okay, so once the location is fixed or once the target is located, it will arrange the control circuitry within the antenna will arrange in such a way that it should focus onto the receiver, or the beam should be focused on the receiver or the target. Okay, so that is nothing but beam steering. So the smart antenna should locate the target and then steer the beam in such a way that the maximum directivity occurs or optimize the directional pattern of the beam. Okay, that is the there are two types of smart antennas. You will see both of them one by one. First one is switched beam smart antennas. The name itself suggests that. The switched beam smart antennas are designed so that they have several fixed beam patterns. Okay. Smart antennas. So antenna is first the antenna is located towards the front. Antenna beam is located towards the front. So total it can locate 360 degree any point it can locate. Then it can turn to right side, left side, like that. It can, the inbuilt circuitry will be there based on the direction of direction estimation. The antenna beam can be turned. But in switched beam smart antennas, there will be some fixed positions. Okay. Suppose this is 0 degree, the next switch will be for 15 degree, next for 30 degree. Like that, it can complete within 15 degree intervals, it can complete the total 360 degree rotation. Okay, it will not be a smooth one. Switch from one position to another position. Okay, suppose the antenna was located straight, that it was located at 0 degree, and the receiver is located at 12 degrees. What the antenna will do? It will switch from 0 to the nearest point which it is having with respect to the direction. So the direction is estimated at 12 degree. So the nearest point is 15 degree. The antenna is having 15 degree. One switch point is having at 15 degree. So antenna will switch from 0 degree to 15 degree. Like that. Okay. That we will see what is written here. The control elements within the antenna can select the most appropriate one for the conditions that have been detected. That's just the example I told already. Okay. So if the location is at 12 degree and antenna is having only 15 degree switching, then it will move from 0 degree to 15 degree, since 15 degree is nearer to 12 degree. Then suppose another receiver or the receiver changed its position to 29 degrees. Then the antenna will switch to 15 plus next 15. It will shift to 30 degrees since it is nearer to 29 degrees. So it is jumping from one position to another position. In between, it cannot locate any positions. Okay. Although this approach does not provide complete flexibility, it simplifies the design and provides sufficient level of adaptivity for many applications. Okay. That is the thing here. This approach does not provide complete flexibility. It is not completely flexible because this directivity of antenna or beam of antenna can switch in between some fixed positions only. It cannot switch to any position between these fixed positions. Okay. So it is not completely flexible, but this design is simple. Okay. Suppose for 360 degrees, we can fix some 12 points or 8 points like that. So the design will be simple. But one disadvantage is that it is not completely flexible. So if the receiver is located in between these two fixed positions, then that directivity will be, we have to compromise on directivity. The overall goal of the switched beam system is to increase the gain according to the location of the user. That we already saw, just some more explanation itself. However, since the beams are fixed, the intended user may not be in the center of any given main beam. Okay. That means if the user is at 12 degrees, is located at 12 degrees, the switched antenna cannot correctly focus on him. It has to focus at 15 degree. Okay. So that is the next switch position as available. So the user will not be at the center always. If the user is at the center only, that maximum efficiency will be there. But the center is at 15 degree, but user is at 12 degree. But since even though he will get a better reception, but the gain will be, or the efficiency will be not 100% or not maximum. Okay, that is a disadvantage. So this is the example of that. So this shows the fixed switching positions. This is the beam, active beam. It can switch from here to here, 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 like that. Only this much fixed positions are available. So if the user is lying here, means, or if the user is here, means he will not be getting a better reception. But if the user is here, he will get 100% because it can switch from here to here. If the user is here also, means he will be getting a lower quality reception only. So that's the thing with this switching beam. Next one is the adaptive array smart antennas. Okay, that you can expect what that can be. See, adaptive array smart antennas allows the beam to continually steer to any direction. Okay, in our switching, the beam was switching from one position to another position. But here it is not like that. It can move, can steer smoothly, or continuous steering is possible. Continuously steer to any direction to allow the maximum signal to be received. Okay, so the maximum efficiency will be there, and it can eliminate any interference also. Okay. They can direct the main beam towards the object while suppressing the radiation in other directions. Okay. The main beam will be fully focused to the intended object, and all other radiation patterns will be suppressed. Because of the ability to control the overall radiation pattern in a greater coverage area for each cell site, adaptive array systems are greatly increased capacity. Okay, it is understood. Since it can particularly locate a user and directly transmit to this, it will increase the capacity. Adaptive array systems can locate and track signals and dynamically adjust the antenna pattern to enhance the reception while minimizing interference using signal processing algorithms. Okay, adaptive antennas are using signal processing algorithms, particularly locate the user and dynamically adjust the antenna pattern to enhance the reception. Just things which are similar to our switching position, but here the thing is it can do it continuously. So this is the difference between a switched scheme and adaptive scheme. Okay, so here you can see user 1 is located here, but since it is a switched scheme, it cannot completely focus onto the user. It can focus into the nearest available location only. The nearest available location is this, but user is here, and user is surrounded with two interferers also. So this minor lobes will be having interference with these interferers. Okay, then this is the adaptive scheme. In the adaptive scheme, even though the user is located at one end or any random position, the main beam can be completely focused into that user. And additionally, what it can do, it can identify the interferers. You can see two interferers here, and the minor lobes which are interacting with the interferers can be suppressed by the adaptive algorithms. So two advantages are here. The main thing is it can directly focus on the user which is located at any random position, and secondly, can identify the interferers and it can suppress the radiation patterns towards the interferers. Okay, so that's all about switched scheme and adaptive scheme. Okay, so next we will move on to the antennas for mobile base station and handset. Okay, these are the most commonly used antennas, and even though like all of you are currently using this with your mobile phones, if you are using your mobile phones right now, you are currently using these antennas. For terrestrial mobile communications, the frequencies range from 200 MHz to 60 GHz. In cellular mobile communications, frequency range from 800 to 1000 MHz and 1700 to 2200 MHz. This cellular mobile only you are using. Okay. So this in sixth module we have discussed this thing, how the cells, reusage of cells and all, how the cellular mobile communication is working. That we already discussed. Okay, even though that is there is no need to discuss that because that is understood. But still we will have a look. In mobile communication, the base station antennas must be highly directive and handset antennas must be compact. Okay. Mobile communication, that is the basic thing. The base station antennas must be highly directive. Means it has to concentrate on the cell which is provided for it. Okay, in cellular communication, the entire area is divided into separate cells, and one cell will be having one particular frequency, and one cell will be having one particular antenna, and that particular antenna will be concentrated to that particular cell or that particular area. Okay, all those things you already know. And what is about handset antennas? Handset antennas must be compact, should be small in size. Then only we can accommodate it in a handset or in a mobile. Okay, so these are the requirement of base station antennas and handset antennas. Base station antennas can be large, there is no problem, but it should be highly direct. So we will see base station antennas. They should direct the signals to the wanted coverage area as effectively as possible. Okay, that is our wanted coverage area means our cell. Okay, this base station antenna should direct the signal to the cell as effectively as possible. But the distribution of power must be restricted accurately in order to minimize the frequency reuse distance in the system. Frequency reuse, we already saw frequency reuse. I think you will be like knowing already frequency reuse, because in a cellular system, since the area is divided into cells, distant cells can use same frequency. There is no problem. Okay, no interference will be there. But in order to happen that, the power should be minimized. If you are transmitting on a very high power, means this frequency reuse for frequency reusage, it will be like we have to consider a very large separation between two cells having the same frequency. The frequency reuse won't be that much efficient if we are transmitting on very high power. So power should be minimized so that effective frequency reuse will be possible. If you are using a high power means, suppose I am using a very high power on a particular frequency. Then since I am using very high power on that particular frequency, that frequency will be having an effect over a wide area outside itself. Okay, so the next point where I can use this same frequency again, that will be a very distant point since the power of this particular frequency is more. Okay, in order to minimize that, I have to minimize the power so that within a near range itself, I can again reuse that same frequency. Okay, so that is there. Base station antennas can be classified into adaptive and non-adaptive antennas. The adaptive antenna changes its parameters to improve SNR value. These adaptive antennas are only we are using right now. These adaptive antennas are using a signal processing algorithm so that it can change the antenna parameters to improve signal to noise ratio value. SNR is signal to noise ratio. Okay. In non-adaptive base station antennas, the antenna performance is fixed and won't change according to the instantaneous requirement of system. Okay. I'll tell you just one example for this adaptive antenna. Okay, in adaptive antennas, you can, don't know whether you have noticed or not. Suppose if you are having a low range, okay, you are having low range or low network coverage in your area, and you are moving to some height or some distance where better coverage is there. There you will get better signal. And from there, if you are coming back to the same position, then still you will be getting some signal. But previously, when you initially come to that position, you won't be getting that signal. Suppose inside your house, suppose you are inside your house, there is no signal at all. But in your veranda, okay, in your veranda, you are having some like small signal you are having, and on the road better signal is there. So initially you are inside your house and you came to veranda, you are getting only very weak signal. So you went to road, then you are getting better signal, like full coverage you are getting, and then you are coming back to the veranda. At that time you can notice that you are getting a better signal than previously you got. And then you just go inside the house, then also you will be getting small signal. Initially it was not at all there. So that is the adaptive adjustment of the antenna to improve signal to noise ratio value. Okay, so that is the like real life example which you can experience. Okay, so this is the base station antenna. This all of you might have seen already. Everywhere it is there. Okay, nowadays it is there everywhere. This is the base station antenna. And handset antennas. I don't need to tell much about handset antennas. This is portable telephone systems require compact, lightweight, and high performance antennas. Like these are the some antennas used for handset in any handset. These are the example of antennas used in handset. External antennas, retractable whip antenna and helical antenna. So these antennas external means it will be visible externally. Okay, we can see these antennas outside. This walkie-talkie and all you might have seen in that one like metal rod is extended outside. That is a retractable whip antenna. And in cars and all you can see this whip antenna. Then internal antennas, planar antenna and chip antenna. The chip antenna are only now we are using. Okay. Initially we were using the strip antennas, microstrip antennas, and now we are using chip antenna. Okay. So now this is the example of whip antenna. See, whip antenna in the car. Nowadays also it is there in cars. This is whip antenna. Retractable. Retractable means it can be like compressed and it can be elongated. So So that is retractable whip antenna. So these are the antennas used in old Nokia phones. It was microstrip antennas. Here microstrip antenna was there, and it was visible outside also. This was helical antenna was used here. Okay, retractable antennas. Okay, so these were the olden days. This in cars and all nowadays also this is using, but in mobile sets it is not at all being used now. Now we moved on to chip antennas. Okay, so this is the current latest technology. Chip antennas are only used. You can see only chips. No antennas you can see outside of this mobile handset. This is the latest Samsung handset antenna configuration. See how many antennas are there. For Wi-Fi, one separate antenna is there here, and for 5G, 5G is not at all here, but I already told this is the latest, most modern antenna configuration. So this is the Wi-Fi. For Wi-Fi, one antenna is there. For 5G, one antenna is there, and diversity antennas are here. Okay. Then another 5G antenna is located here. Three antennas, low to mid-band carrier aggregation for all those purposes. Three antennas are located here. Like so many antennas are being used in a single handset, and all are chip antennas. Very, very modern antennas and sophisticated antennas. So, like you can see, you are already using these kind of antennas. At least your phone will be having this Wi-Fi antenna and a 3G antenna, or all phones are 3G phones right now. Okay, and these antennas are also will be there, diversity antennas and this low to mid band and carrier aggregation. These three antennas will be there in every smartphone as now. Okay, so with that we are coming to an end of our session. Okay, so let me just take your attendance. The attendance is less only. Okay. So I think our syllabus is completely finished. So this is the last class which I am going to take for this semester. I hope you had a nice time, and wish you all the best for the university examinations and all. Okay, so thank you for listening to the class.